Suppose a communication network fails, the users of the network will not be very happy. Always we have to ensure that the network is functioning properly. So, in a communication network, when the links fail, either the link is actually disconnected or the link is highly congested with the data, then there may be a failure. Okay. So, when designing a communication network, the major focus is to avoid or to minimize these failures. Okay. So, in a communication network, people will try to avoid a bridge which is just a single edge. The failure of a single edge will make the network to fail, okay, and try to avoid many cuts. If we have so many min cuts there, min cut is actually partitioning the vertex set into two parts such that the edges between the two blocks of the partition is minimum, correct. When you remove the edges, the graph is going to be disconnected. So, if we have the size of the min cut as a small number in a network, or if you have so many min cuts in the graph, there is a high possibility of failure. Okay. So, you have to avoid that one. So, this is one application of min cut, and you design the network itself, you can analyze and see whether you are having lot of min cuts or what is the size of the min cut. These two measures are going to be important. Okay. What is a highly connected graph? You have learned the edge connectivity of a graph. Okay. So, edge connectivity is nothing but the minimum number of edges whose removal results in a disconnected graph. Okay. Now, if in a graph, if the edge connectivity is greater than n by 2, then it is a highly connected graph. Okay. Then the minimum cut size is going to be, what is the minimum cut size? Greater than n by 2, correct. So, there is an assurance that failure of one or two edges will not make the network to fail. Okay. So, this is one simple application of min cut problem. Next one is a web graph model. I think all of you know about web graphs. So, how do you model that web pages and the hyperlinks? You can take a web page as a node of the graph. If there is a hyperlink from one web page to another web page, you join it by a directed edge, correct. So, the resultant one is a directed graph. So, this is a simple example of modeling the web pages. See, this is actually 2007 World Wide Web, this is given by that Google. So, it is a very complex network. Web graph model is a very complex network. Now, where comes this min cut? Okay. So, this size of the minimum cut provides a measure for how much groups of pages have related content. Okay. So, when you search for one topic, the related web pages should be displayed, correct. So, you can actually use this idea, it is for clustering, okay, or grouping web pages of similar content, correct. But there are lot of data mining algorithms for clustering and all. This is a basic idea how to use the min cut algorithm to do the partitioning or to cluster the web pages into blocks where each block contain similar contents. And see this one, this idea, can you use it in the social network for community detection? How do you model the social network? Each user as a node of the graph, correct. Then how do you form the edges? Friends, okay. Then you will be having a very huge complex network, correct. There also you can make use of min cut idea to do clustering, okay. Groups of people or say community of students or people having similar interest. But what happens, the graph min cut idea is already there, but there are some limitations for applying this graph min cut problem to social network while finding the community direction. The reason is you can have sometimes isolated vertices after doing the clustering, okay. That is the reason why lot of other measures related to centrality measures related to graphs are introduced, and they are also utilized in doing the community detection. Just this graph cut idea alone is not sufficient to do an efficient community detection. Next application is image segmentation, okay. So, this is one basic idea in image segmentation. What is image segmentation refers? It is a process of partitioning the digital image into multiple segments. Why do you want to actually do the image segmentation? Further manipulations you can easily do, you can change the representation of the image and you can actually process that one easily if I could change the representation in a meaningful way. Okay? And normally while doing the image segmentation, similarity, that is the gray level difference, and proximity, how to group actually similar objects there, and continuity are important factors. Today I am going to show you by how using similarity how a graph is constructed from an image, and using the min-cut idea how you do image segmentation. Okay. So, first you should know how to represent the image as a graph. So, you can have actually the feature space of the image. The feature space is represented as a weighted undirected graph. Now, the points of the feature space are taken as the nodes of the graph. I will explain it with an example. Then edge between every pair of nodes. Then some weight has to be assigned. The reason is lot of similarity. For example, if you take the similarity measure, between 2 pixels you may have lot of similarity. Between 2 other pixels you may not have much similarity. So, we can assign that one as a edge weight. Okay. So, the edge weight Wij is a function of the similarity between the nodes I and j. Now, what is the problem? Problem is you partition the set of vertices into disjoint sets, correct, or blocks such that there is much similarity within the blocks and very low similarity between the blocks. Are you able to understand? Is it a min-cut problem? So, the problem I will repeat, you partition after constructing the graph, you partition the set of vertices into disjoint blocks such that there is much similarity within the blocks and very low similarity between the blocks. Okay. Now, see this is an image. Okay. So, it is the gray level is considered, each pixel is going to be represented as a node of the graph. So, these 4 pixels are represented by 4 red nodes here, and these pixels are represented by the blue nodes. Okay. Now, additionally you add 2 nodes F and B like your S and T in a ST network. Okay. So, here F stands for the foreground and this is for the background. Okay. Now, when you consider this one, then you can add actually, see in this case it is a weighted graph, but I did not include the weights as numbers. From the thickening of the edges you can understand which one is having more weight. Okay. So, see F it is written in the form of a matrix like this, F B, F B, then F B, F B and B, correct. What do you expect finally after image segmentation? All F's together and all B's together. You have to partition the graph like that. Okay. The image has to be segmented like that. Okay. Now, for that you can add 2 additional vertices F and B. Then see you can put edges between these pixels and this F as well as B. This thickness of the edge represents the similarity. Now, for example, this node if you consider, and I have taken actually this node F as the foreground, correct. Now, this is having much more similarity compared to this node. So, this edge thickening is more. Similarly, when you consider this B node, this node is having more similarity and hence this edge is thickened, correct. You are able to understand this construction. Then put one edge between each pixel. So, between each pixel we are adding the edges. So, it represents the image, this part, am I correct? 3 by 3 image. Okay. So, what happens to these edges? If there is a similarity, the edge weight is more, correct. If there is not much similarity, the edge weight is less, Are you able to understand how you are able to represent the image? So, it is a weighted undirected graph, correct? And you consider this lightweight, see this is not having much thickening, so this is deleted and this is removed, correct? Like this actually we are removing all lightweight edges, correct? It corresponds to a min cut. So, after doing the min cut, what happens? These pixels are grouped together, correct? This is in one block and these pixels are in another block. So, the outcome of this algorithm is, in terms of the image, this one, this is the segmentation result, this is in one block and this is in another block. Are you able to appreciate? Okay. So, it is not, the process not at over, correct? This is only a starting point, correct? After doing this segmentation, you can do lot of image processing. So, this is a basic step which is utilized in image segmentation. Okay. So, we are using min cut of a directed unweighted graph. So, that global min cut algorithm you have discussed, slight modification of that one by adding the weights can be utilized here. Okay. So, this I have taken this one from image segmentation using minimal graph cuts by Anderson. This is a research paper. So, if you are interested, you can refer this paper and learn more and more. So, I have introduced briefly some applications of min cut. Okay. Then some open problems related to min cut. In randomized algorithms area, you are having lot of open problems, but I have projected only 2 open problems related to min cut alone. Okay. The first question is there a randomized algorithm for min cuts with the expected running time close to order of m? It is not very easy, it is a research problem. Okay. So, is there a randomized algorithm? First you have to answer, is it possible or not, correct? When you do comparison based sorting, what is the least time needed? N log n, correct? Theoretically it is proved, correct? So, you cannot do below n log n. So, similarly, is it possible to have a randomized algorithm for the min cut problem with the expected running time of order of n? When you do the expected running time, naturally you can expect the algorithm to be a Las Vegas algorithm. Okay. Then the second question is, devise a Las Vegas or a deterministic algorithm for min cuts with running time close to order of n square. Okay. Kargar's min cut algorithm order of n power 4, correct? Then its improvement order of n square log square n, if you repeat it for log n times, correct? Now, can you devise a Las Vegas or a deterministic algorithm for min cuts with the running time which is very close to order of n square? So, if somebody is interested in randomized algorithms part, they can try to do. So, if you can achieve this one, it is a breakthrough. And if you refer or browse, you can actually see lot of open problems. Now, a little bit about actually Las Vegas algorithms also. In the randomized algorithm part, I have introduced what is a randomized algorithm, then discussed only Monte Carlo algorithms. What is a Las Vegas algorithm? Which produces the correct output. What running time is going to be a random variable, so you will be computing the expected running time. One simple example of a Las Vegas algorithm is randomized quick sort. Are you familiar with randomized quick sort? Okay. So, it overcomes actually the weakness or the drawback of the deterministic algorithm. What is the worst case input for the deterministic quick sort? Already sorted array, correct? So, but when you run the randomized quick sort, you need not be worried about the input distribution. It may be a sorted array, no problem, correct? On the average, it will take only order of n log n time and produces the correct answer. So, I would like to add on some more points related to this Las Vegas algorithms and conclude my session. Monte Carlo algorithms, already we have discussed 2, so I think you are familiar with the Monte Carlo algorithms. For the Monte Carlo algorithms, you have to do the probability of success, correct? Analysis of probability of success. Now for the Las Vegas, the correctness you have to prove. You can prove one theorem and finish it off, okay? Then do the expected running time analysis, okay? In graphs also there are lot of Las Vegas algorithms. One such algorithm is for the minimum cost spanning tree problem, okay? What are the algorithms known to you? Prim's-Kruskal's algorithm, etc., correct? But the beauty of this randomized algorithm is it runs in almost linear time. It is in order of m plus n, okay? I am not going to discuss the algorithm, and it is due to Karger, Klein and Tarzan in 1995, okay? If you are interested, you can even refer that randomized algorithm books by Rajiv Motwani and Prabhakar Raghavan, okay? It is available in that book itself. It is a nice work. If you are interested, you can refer that one. Now, okay. So, you can design Monte Carlo algorithms, correct? How do you convert that Monte Carlo algorithms into Las Vegas algorithms? Can you convert that Monte Carlo algorithms into Las Vegas algorithms? See, for Karger's min-cut and that fast min-cut algorithm, we have repeated the runs, am I correct? What is the purpose? Purpose is to reduce the error probability. If you can reduce the error probability to a very small number and probability of success is almost 1, then it becomes a Las Vegas algorithm, correct? So, people will be repeatedly running that algorithm and trying to convert it as a Las Vegas algorithm, okay? So, in general, in randomized algorithms part, both are equally important. But if you can design a Las Vegas algorithm initially itself, you can be very happy, and the expected running time should be a polynomial one, okay? But if you get a Monte Carlo, you try to convert it into a Las Vegas by repeatedly running it, okay? For that, to reduce the number of runs, we need the success probability of the algorithm to be high. So, you got some idea. I would like to conclude with this one. I do not want to dump so many things in the last session. Some of the references I can give, and last one is actually a research paper for that image segmentation problem I have taken. With this I would like to conclude, okay. Thank you so much.